Good morning, and thank you for sticking by. So I'd like to also start out by thanking the organizers. I had a fantastic time both last week and this week. So this will be on the light side, and it will be relatively short. So I thought that I'd talk about something that connects to the topics of the conference, even though the most important element, cavity, will be missing. But optical control is there. So these are the people involved in, this doesn't work. Here it is. So these are the people, my collaborators, and we got the samples, from Shadong Xu and Eric Anderson, and the experiments were done by my PhD student, Olivier Huber, and a former postdoc, Tomasz Smolensky. But the real credit should go to Tomasz for the what I'm going to tell you about. All right, so I thought I will keep the introduction short. I thought I sort of present a golden braid for modern condensed matter physics, or the topics that are of interest and that we also covered here definitely include strong correlations, topology, and as we just heard from Sebastian, non-equilibrium physics and laser-driven systems. And basically, we heard about sort of phenomena that connect these corners, like fractional Chern insulators, light-induced superconductivity, light-induced ferromagnetism, as well as Foucault topological insulators on this side. So what I would like to sort of bring up is maybe a topic that could combine all these three and pursue optical control of topologically ordered states. Okay, so if we proceed. So basically, also within this conference, we have heard different approaches to optical control. So I guess one of the most established ones is, for example, as presented by Andrea, is the strong coupling of pulse lasers to electronic, or in his case, the phononic degrees of freedom, to generate what he calls light-matter hybrids. Okay? So in this scenario, you could have either a transient response, so light-induced superconductivity, which persists practically as long as the drive persists. But in some cases, and I do not understand it, but what they also see is that there is a quasi-metastable response, that they drive strongly, turn the pulse off, and you can still have a quasi-metastable effects, and this was the case, for example, in light-induced ferroelectricity. So the other possibility is to consider either a CW periodic drive, so this is the standard for Foucault systems, or as in this conference we heard many times, one can enhance the vacuum field or perhaps the static fields, and in this way modify the material properties or control material properties. And again, one example here is what we heard from theory. So James's results was really pulse, right? So that's is not, even though it was a fantastic example of Foucault topological insulators. Now, there is actually another way of controlling quantum systems, and that would be, again, also in the spirit of what Sebastian was talking about, to consider steady state of weakly driven dissipative systems, and this could be under a continuous wave drive. Okay, so in certain classes of these optically controlled systems, the ordered state exists only when the drive is on, and that's a polariton laser or a regular laser for that matter. And then there are other examples when the ordered state persists practically forever and after the drive is turned off. Okay, and the first example I learned about this is atoms pumped into a single hyperfine state. Okay, so let me say a few things about this last category. So the history really goes back to 1950s, Alfred Kastler and Grossel, where they basically showed that even before lasers, by pumping the system with circularly polarized light, you can prepare atoms in certain hyperfine states. And when they reach these hyperconfined states, then probably your vacuum would be leaking before they find their way down to the lower energy states. It's really very metastable. And the other example on the solid state side is something also mentioned by Andrea, is the Overhauser effect, that one can use actually nuclear sort of electron spins, polarized electron spins, and then transfer the polarization from electrons to nuclear spins. And again, this can be a very long-lived metastable state, and in some cases actually, like in quantum Hall states, the polarization of nuclear spins do take place even without an external pumping. Okay? And the basic idea here is that you transfer the spin angular momentum from photons either directly to atoms or through electron spin by making use of spin-orbit interaction to create these metastable ordered states. Okay, so now the question that I'm going to address here is we have seen that topological states or Chern bands exist at zero magnetic field, and these are associated with degenerate single particle Chern bands where the time reversal symmetry is spontaneously broken due to interactions. So the question then is, can we start out with such a system and use optical pumping to modify the Chern number of the underlying minibody states? Okay, so this is the outline. So I will first tell you briefly about twisted molybdenum, a material system that has become extremely popular in the last 2 years, thanks to advances by my colleague Xiaodong Xu. And I will not discuss sort of TMDs or 2D materials in general, because we have already heard nice reviews of this. Then I'll show you a poor man's optical control, basically how one can change the Chern number of an insulator, Chern insulator, from 1 to -1 or vice versa, using not a CW laser, but a filtered white light. Okay, so looks like, and what we find is that the effect can be rather robust and doesn't require lasers. And then I'll tell you what we intend to do next in terms of coherent control and why this is interesting, as it does allow for defining edges all optically rather than using gate electrodes. All right, so the bilayer twisted molybdenum device, again, as I said, this device was, or two devices were given to us by Xiaodong Xu. So the idea here is to take two layers of molybdenum, do R stacking at an angle around between 3 and 4 degrees. Okay, so this is how the micrograph of the device looks like. Now, what is important is you have already seen moire physics. So in such a structure, basically we have these 3 high symmetry points, and the points where the metal atom in the bottom layer lies below a chalcogen atom, or the opposite. These are 2 of the high symmetry points. And basically for the valence band holes, in the top layer, the XM site is better. So basically, if we have holes in the top layer, if the layer energies are different, then they will be sitting at these XM green spots. And then the opposite is true for the bottom layer holes. They would like to occupy these orange sites. So if there is hybridization between these 2 layers, then basically we'll have a honeycomb lattice, and we would be relying on hopping of the holes from these XM to MX sites and so on. Okay, and it is really this presence of sizable interlayer tunnel coupling that is essential for the emergence of the valley contrasting Chern bands. Okay, so this is the only equation I have. So I really like it, so that's why I want to show it. And I don't like writing equations in transparencies by LaTeX, so it's all handwritten. So basically, again, if you look at the Brillouin zone, so we have this disappeared, the moire Brillouin zone that is defined with the sort of high symmetry points. I don't know why this is not working. Okay, at kappa plus and kappa minus, or kappa top and kappa bottom. So I cannot show you now. Maybe there's a laser that I could use in parallel. Yeah. All right. So, and then the original k and plus k and minus k points of the underlying Brillouin zone essentially become a spin-like degree of freedom. Okay. So now the Hamiltonian is nice. So basically we have this tunnel coupling between the layers. There's a moire potential for the top and bottom layers that is displaced, but otherwise identical because of the symmetry in the system. And then what is really essential is the fact that, you know, for the top layer, the minimum of the dispersion, if you will, is at the k plus point, whereas for the bottom layer, it's at k minus point. And twist means there's a finite momentum difference. Now, you can think of these as basically gauge potentials. And the fact that, you know, normally if it was just this layer, that's a constant gauge. One can gauge it away and it's irrelevant. But the fact that the two layers have different gauge potentials means that this is real and you cannot get rid of it. There is an observed phases, hopping phases associated with it. And it is these hopping phases that is essential for the destructive interference that leads to the Chern bands, flat Chern bands. Okay, so that's all the theory. So this is how one can think about it. So basically, as we, let me try this here, as we go around in the real space, what we would have is that I told you that the minima for holes in the top layer, I'm getting confused, is at the XM sites, and for the bottom layer, it's at MX sites. Okay, and as we go around in the unit cell, moire unit cell, the layer pseudospin will go around, right? So at XM sites, it will be pointing up, top layer, and at MX sites, it will be the bottom. And in between, one can show that this layer pseudospin covers the whole unit sphere, okay? And that provides a strong indication that one has topological bands. This is a calculation from Wu and McDonald that really is a pioneering work from 2019. And as far as I understand, it's wrong, not conceptually, but in terms of the predictions because of the DFT model that they have used. So the story is that you indeed get these sort of lowest or highest energy bands in valence band, moire bands that are plus and minus 1 Chern number only for higher than 3 degrees. At low angles, you actually have a more complicated scenario. Okay, but doesn't matter for us because we're doing experiments, and then what is important is that you end up with flat Chern bands. And this would be the second equation. I forgot but I'm not going to use it. So, all right. So let's look at the scenario. So if you have a neutral system, time reversal symmetry is broken. I'm not going to consider, let's say, physics at finite magnetic field. I will only use magnetic field to initialize the system. Okay? So basically, what I have then is that I have these two Chern bands. I don't know what I have in the conduction band. Looks like the hopping is weak, and there is really not so much of a hybridization for the conduction band space. But that's not important. So we have these Chern bands. Both are empty or fully occupied by electrons. And that's not so different than when it comes to exciton physics than a monolayer. And the reason for that is that the excitons are very strongly bound. So these layers separations that are indicated here are on the order of tens of milli-electron volts, whereas the exciton binding energy is 200 milli-electron volts. So that means that when I form an exciton, it's not just in one Chern band. It's in a superposition of many Chern bands. Right? So in this case, I would say without holes, the physics is boring. But once we hold up the system, then we will see that the system spontaneously breaks time reversal symmetry. Okay, and this can be understood as due to exchange interactions favoring the holes either to occupy, let's say, the K minus valley or plus K valley. In this case, I chose the K plus valley. Okay, and we'll see how this can be changed. All right, so how do we know this? So we know this from Shadong's experiment. So this is from their publication about 2 years ago. What they did is they looked at let me comment on that later. So, and maybe I'll show you the data and you can tell me what the role of ferroelectricity might be. I think that the system is actually multiferroic in certain regimes, but I'll come to that. So this is the result from Shadong, as I said. So it's photoluminescence. It's not terribly interesting, I guess. What I'm showing here, though, what I should really mention that this is photoluminescence in sigma plus. So if you look at sigma minus at low powers, you don't see anything, okay, or very weak photoluminescence signals. That's okay. So that suggests that indeed there is valley polarization. But what is more interesting is these cusps or blue shifts in photoluminescence at certain filling factors. When magnetic field is 0, this occurs exactly at nu equals 1 and nu equals 2/3, okay? As you increase the magnetic field, what they saw is that the density for which this cusp occurs, indicating that the system is incompressible and has an incompressibility gap that is comparable to this trion binding energy. So this luminescence can be considered as attractive polynomial trion, and this again have been introduced already, so I'm not going to talk about that. But basically, once the gap is larger than the trion binding energy, then the system is having difficulty in dressing the exciton by creating excitations out of this Chern insulator state. Okay? So that's the reason why there is a cusp. But what is really interesting, of course, is that the cusp shifts to higher energies. This is our data for our sample. You see that there is a shift towards higher densities, where the maximum of the PL energy is, not PL intensity. And you can map this as a function of magnetic field, and you see that it nicely follows the Schroeder formula. Yes, Mama? Yes.
Would have been correct if the total intensity of the PL would have been constant. But the non-radiative decay rate is also dramatically changing because you're going from bright to then dim.
I don't know about the non-radiative decay rate, but I would say that actually forming trions, if the formation of trions is more difficult, I would also expect not only a blue shift, which is essentially tells me that dressing is reduced, and therefore the quasi-particle weight of these excitations is reduced, but also that the excitations might find other ways to recombine before. So this I'm just showing. I'm going to, as you know, I'm a reflection person, so I will only show from now on reflection data. So this was more historical.
Oh, I see. I was surprised.
Yeah, no. All right. So I haven't converted. So anyway, so this is basically showing that even in our device, which has 4.1 degree twist angle, which is really on the high side, we see the Chern insulator state. All right. So now, as I just said, we like to do reflection measurements, and that's also what we did in these devices, which is what you see on the right-hand side, right? And looking at it, maybe you would say, what does this mean? So what should we get out of this? And to basically, although I claim here that the fact that sigma plus and sigma minus are so different is already telling us that there is time reversal symmetry breaking, right? So the system responds to one polarization in a or to two polarizations in a fundamentally different way. But for you to make more sense and to make my point about quantitative measure of the valley polarization, let me remind you what happens in a monolayer, in the boring case. So as you inject electrons or holes into the system, and this was mentioned already, the exciton becomes a repulsive polaron. It blue shifts due to effective repulsive interactions. And then there is a new attractive polaron branch, which you can think of it as a collective excitation of trions. Okay? So that's the simple picture there. What is really nice, though, is that this picture provides a very good measure. And the way one can see that is go to high magnetic fields. And at this 14 Tesla, what happens is that up to about 10 to the 12 or higher, all the electrons in this case that we inject go to one value because of the Valley-Zeeman effect that Ajit first observed. Basically, the energy of electronic states in K minus valley are lower. So when we inject, all the whole electrons go to K minus. Now, if you look at excitons that you generate, or excitonic spectrum, when you generate an excitation in K plus valley, then you see this repulsive polaron and attractive polaron formation. But if you try to generate excitons in the same valley as the electrons are, you see nothing other than a blue shift of the line. Okay? So that's the reason for that is to form a trion or attractive polaron, exciton and electron have to be, or exciton and hole, have to be in opposite valleys. Now, you can turn it around and you can actually show, using a Chevy analysis, that the oscillator strength of this guy is linearly proportional to the electron density with coefficients that actually are known. Okay, so now basically what this says is that we can actually look at the strength of the sigma plus and sigma minus transitions and determine the degree of spin polarization in the system. All right, so now let's go back and let's first look at this density dependence. And what you see now, to guide you, I put down these attractive polaron, exciton, and repulsive polaron indices. So of course, when there are no charges, sigma plus and sigma minus are identical. When I introduce charges for low filling factors, you see that you have attractive polaron in both polarizations, but beyond about nu equals 1/3, this guy disappears. This guy gets really strong in sigma plus for this particular experiment. And then you see that it remains polarized in one valley, and that's why we see attractive polaron only in one valley. Okay, so we can also keep the density fixed at nu equals -1, so such that we are in this Chern insulator state, as we have seen, and then vary the applied field. So you may not have noticed, but in this Hamiltonian that I showed you, the electric field enters because it changes. These are identical layers, but if I apply a displacement field, I change the energy of the two layers and therefore influence how well they're hybridized. Okay? And what you see here is that as a function of this applied displacement field, there is a finite range in which you see this complete valley polarization, and beyond which actually you start to see attractive polaron formation in both layers. So the question that you are raising is, this scenario is there is no ferroelectricity at zero field. What can we say something about some polarization? Is it spontaneous? This I do not know, but this is the data. All right, and we have two attractive polaron resonances, two exciton resonances. That's because the two layers have slightly different strain, and therefore there are two resonances. But the two resonances seem to hybridize, and that's why one resonance is substantially stronger than the other. And we don't fully understand that part. All right, so this is a second device, which is in the better range of 4.5. This is very close. So I should have said 3.5. That's wrong. So this is 3.5 degree. This is very close to the twist angle for which the bands become almost exactly flat, according to calculations from Junkai and Ashwin. Okay? And you see that the spectra looks nicer in this device, and I won't show any more data because our magnet broke shortly after. But you see that now this attractive polaron has a cusp, not a very sharp cusp, but a clear increase in energy at nu equals -1, which is consistent with this suppression of screening that I talked about. Yes,
so Atac, what's the cross-polarized peak at higher energy in the sigma minus?
the cross-polarized, this one.
No, in the left, yeah, that one.
This one. So this one is the exciton or the repulsive polaron. This should be the counterpart of this guy, right? So this is at much higher energy, and it is actually not so much higher than the exciton, the bare exciton, but it must be. I mean, I must say I haven't looked at it, but it's 1140, yeah, 1140. So it must be this feature that we also do not understand.
But if you go back one slide, I think it's there in your first sample as well, right? Yeah, there.
Yeah. I think that here this crossing is not as visible, but it's there. So this is a feature of nucleus -1 and nucleus -2/3. So it's a signature of incompressibility that we do not understand it. Okay? So,
thank you.
As you move away from nucleus 1, this cross enhancement disappears, and it is not interlayer excitons. That's what we initially thought, because the slope is much smaller than what you would expect from this dipole of 7. Yes?
Sorry, I have a very naive question. So flat bands basically imply that the carriers are localized, right? So in space. So when you form your exciton, maybe it's a theory question, is it also localized?
No, the reason is I try to point this out. My excitons are extremely tightly confined. They have a Bohr radius of 1.5 nanometers. So the effective magnetic length in the system, because we have unity flux in each moire lattice site, is about 4.5, 5 nanometers. So my exciton, because of the strength of the electron attraction, is very strongly localized. That's only possible if the exciton is formed by a superposition excitation of many moire bands. So in that sense, it is not, I mean, the fact that one band is flat doesn't make any difference. But let me also say that this was all theoretical work by Rice and Ueda from 85, if I remember. So you can actually also consider two flat lambda levels, so like in gallium arsenide, very high cyclotron frequency. The exciton energy, exciton dispersion is not flat, right? And that's due to this magnetoelectric effect.
I'm trying to understand what's the significance of being at the magic angle if it doesn't matter anyways?
There is no magic angle
well,
here.
Not magic angle, but I'm sorry, whatever it is.
I think the importance of that is most likely, so I don't have enough samples to study, but this is when the incompressibility gap is maximum. That's what I would expect. But I don't think there are experiments on that. Definitely not from us, but also not from Shadow. All right. Okay. So now I told you about this measure of degree of polarization, or S sub Z. This is the oscillator strength difference between what you do not see here, and if you normalize it, that gives you basically the electron density difference in the two layers. I'm not sure what I'm doing here. Yeah. So, and that gives you a subset. Okay, so that's how we determine the degree of polarization. And what we then do is to verify that there is ferromagnetism, that we do magnetic field scans, and what we see is that there is a very nice hysteresis curve. And we did this at low power. We changed the polarization of the white light that we study, and there is a minute effect, but basically you see that if you prepare, let's say, spins in K plus value, then as you tune the magnetic field off, they remain there, and as long as we can measure. Okay, and then we can only switch them to the other value at a coercive field of about 50 millitesla. Right. So that says that magnetic field can actually be used and is generically used to prepare this state. Now, This is the regime where the ferromagnetism exists. So it's over a relatively large filling factors. For this sample, starts out at nu equals -1/3. There's interesting structure here. So, you know, as you apply a displacement field, the polarization is enhanced. And then it has these two legs, which are, again, yet to be studied by us or others. All right, so there is a question about, you know, when do we this is where we have layer polarization, and here we lack layer polarization, and, valley polarization. And in this region, we have layer hybridization, and the question is whether this transition exactly coincides when you lose the layer hybridization. That's, I think, something also that needs to be figured out. Anyway, okay, so now let me come to the actual point that I wanted to make. So I showed you the state already at 2 nanowatts, and we now are going to do an experiment where we pump the system with a certain polarization, well-defined polarization, for a few seconds. As I said, it's poor man's pump probe in this case. Then we probe with the probe light with the much smaller power, where we know that the polarization of the light does not matter for a few seconds, and then we look at, you know, what we see in this probe. Okay, so now what we find is something that's really, in my opinion, remarkable. As we go to, for example, in this case, 110 nanowatts, so we completely destroy the hysteresis curve. So for linear excitation, it just shrinks, and it looks like it's a high temperature behavior of a ferromagnet, that it's a super paramagnet. It lines up with the magnetic field quickly, but otherwise it doesn't exhibit any appreciable hysteresis. But if you pump with circularly polarized light, there is again no hysteresis, but you clearly push the transition to finite magnetic fields on the order of the coercive field, and the opposite case for sigma plus. So basically, what that is telling us is that if you sit at zero magnetic field, by pumping with sigma plus, we can prepare the holes in the C=1 Chern insulator state, whereas with sigma minus, we can prepare them in the C=-1 state. Okay? And this exists for a finite range of magnetic field. All right, and just to give you sort of an idea, so this is as a function of pump power, what happens if you start out from a K plus valley polarized holes. You see that for low powers on the order of nanowatts, the light doesn't have any effect. And then as we increase the power beyond 20, 30 nanowatts, we see that with sigma minus polarization, we completely switch the sigma minus polarized light, we can completely switch the polarization, whereas sigma plus remains as is. And this is as a function of filling factor, that again, the effect works wherever we see spin polarization. We can, you know, when magnetic field polarizes the system, then circularly polarized light also does it. And this is a direct comparison. So this is what I showed you before, using magnetic field scanning. This is going back to zero magnetic field. This is where you see ferromagnetism, and this is where you can see optical spin pumping. All right, so then the question is, what's happening? So how do we understand this? We don't, but there is a possible mechanism that I will run by you, and then I will tell you about the mechanism that I do understand but haven't done experimentally yet. So basically what we are doing is that in these experiments, we pump the attractive polaron resonance, okay? So we have the holes sitting in the C=-1 moire band. We excite excitons. They form this attractive polaron, right? And most of the time what happens is that recombines, the system goes back to its normal initial state. But once in a while, the electron can hop from this value to another, okay? And in this way, I can form another trion, or attractive polaron, which now can emit or decay by emitting a sigma plus light. And when it does is that what I have effectively done is transferred one hole onto the other state. Normally, this doesn't happen in the ground state because there's an energy barrier due to exchange for such processes. But optically, I can pay this energy by a shift in the absorbed versus emitted light. And with a combination of such events, I can basically make it favorable for the system to switch the values and form C equals +1 Chern insulator state. So this is very similar to what happens in, again, nuclear spin polarization or atomic sort of hyperfine state preparation. The main difference is there, the atoms are independent, so there is no barrier. Whereas here, for single particle excitations, there is a barrier. It's just that the final states are completely degenerate, right? So this state and this state is degenerate. It's just that you have a barrier, just like in any ferromagnet to get there. Okay, so now the scheme that I like and I'd like to realize, it would be based closer to the topics we discussed here, to use AC Starship, so sub-band gap light to achieve control. So how would this work? So let's consider this. So let's assume that we start out here with the holes. And if I drive this system, the other valley with, say, sigma minus light, then we have seen that I can form an attractive polaron. And if I'm detuned from the attractive polaron, then there will be an AC Stark shift. Okay? And that AC Stark shift would lower the energy of the ground state. Okay? So one should not really think about lowering the energy of this C+1 layer, but rather that the whole initial state of the transition or the ground state energy is lowered. So what that means is that the Chern insulator state becomes even more robust. Okay? But if I were to excite the system with sigma plus light while having the holes in the same valley, then I do not have an attractive polaron resonance, so the AC Stark shift would be much smaller, so therefore there will be a weak reduction in the energy. Okay? Now, if I then consider the scenario with the sigma plus, as I said, this energy is shifted below by a low amount, but if my holes were to flip the valley and all the way to the other Chern band, then they can lower their energy. So the balance between the single particle states is now broken by the AC Stark shift, by the circularly polarized AC Stark shift. Okay? And this doesn't take much. You've seen that the coercive field is 50 millitesla. So all it takes is to really change with the energy of the single particle bands by tens of micro EV in order to sort of tilt the system towards one way. Okay? And what David Ashelholm here about 20 years ago showed is that by using circularly polarized sub-band gap lasers, you can actually generate effective magnetic fields, splittings on the order of Tesla or more. Okay? Okay, there are questions about this will be pulsed and whether the system has enough time to switch. That's what makes the experiments interesting. All right, and the final point is about sort of an application of this. So we think that we can use these ideas to optically define edges in various different geometries. So here, as a proof of principle, what we did is we took a system where we prepared the system in the K minus or C equals -1 Chern band, right? So this is the attractive polaron resonance that you see. You don't see anything here. And there is a variation spatially that shows the quality or lack of it in our device that different places have different resonance energy. So this scale is microns. Okay? But as we excite the system here with the sigma plus light, then what we find is that we transfer the holes in this region and maybe a little bit out because of diffusion onto the other Chern band, and whereas the holes that are farther away remain more or less where they are. So, okay, so this is, of course, a preliminary experiment, but you can see that by playing with the shape of the laser pulse that we excite, we can define edges in a clean system. This would be really nice because then this could be far away from any let's say, electronic contacts or inhomogeneities that you may not have a control over. Because in these devices, typically you have good regions and not the whole 20 by 20 micron device has the same quality. All right, so that's all I wanted to say. So I'll stop here. Thanks.
Questions?
So these excitons and trions, yes, they're kind of analogous to molecules or Efimov states in cold atoms. I guess with a big difference that they are always localized. So is there any way to get them larger or have something like a Feshbach resonance? Or?
Yeah, so they're not like Efimov states because they are, I would say that they're more like two-body bound states, right? So exciton is very strongly bound, so you can think of this as an additional charge binding to it. It's the direct analog of H- ion in atoms. So they are, in principle, delocalized, right? So basically, these are K equals 0 excitations, and therefore, the exciton that we generate extends out, at least in a reasonably clean device, and I'll give you an energy scale, extends out all the way to the optical excitation spot, which is like a micron squared. Now, so how does this happen? So we made these experiments some 7-8 years ago, showing that if you drive the exciton resonant, it's a very good mirror. So a very good mirror means that the polarization that you generate decays radiatively, just like in glass, which is not a very good mirror, but when light comes in, it generates a polarization. It's way off resonance, and it just re-radiates. There is no incoherent process that can take place. So in these systems, the radiative decay rate is so large that the disorder does not have enough time, is not strong enough to localize the exciton. So it remains a K equals 0 excitation. Whether this is also true for attractive polarons is not clear. Their reflectivity is much smaller, but their oscillator strength is also smaller. So how delocalized attractive polarons, these collective excitations of trions are, is not okay.
Maybe making an analogy to MR, and you talk about this mechanism of like optically pumping the system, like would it be possible to extract some information about the rate via time-dependent measurement? Like can you add a delay to the pump?
Yeah, absolutely. This would be, of course, very nice to see how how long it takes to do the swap. So in the AC Stark experiments, this would be a relatively easy way, because then we will use, instead of these Pullman's pump probe, we will use essentially more serious pump probe with femtosecond or picosecond pulses that we excite and then probe. So then we could determine, what kind of time scales is needed in order to do the Chern number fit.
I had two questions. You answered one of them. Okay. The second one was these 110 nanowatt. Doesn't seem too much, but our experience with tungsten is that even 50 nanowatt is a lot, meaning that it would destroy this attractive polaron picture. So in the kinetic magnetism paper that you had this dome. Is the dome still persist even at 110 nanowatts?
So here the situation is different than the dome, right? So basically, dome was there. So Mamad is referring to this different moire system that we studied, where attractive polarons were very strongly localized at moire sites. And so basically, as you increase the electron density up to nu equals 1 half filling, the strength increased, but from nu equals 1 to 2, it just came back down. And the reason for that is, in that case, the electrons, it was, that in order to occupy these sites, they had to form singlets. And once they are forming a singlet, then they couldn't care about the exciton. They would not form a trion, because the trion actually forms by forming, when the electron of the exciton and the resident electron forms a singlet. So it's a bit detailed. So we don't see that here because the system doesn't have, it's in this single valley state, right? So it's not a singlet state. But the answer to your question, so there, because it was a relatively large, I mean, this is my guess, large moire constant and very deep potential, that the deep polarization of the electrons was much easier. So there we had to work with picowatt powers in order to not to depolarize. So this was a nice surprising change that we had to go to 50 nanowatts of linearly polarized light to depolarize. So that's, that's how it is. I think it's really the robustness of the system, and most likely.
No, my comment was that at 110 nanowatts, a polaron picture may actually break down. So then it cannot be a probe of magnetization. That's the comment.
I don't think so. I mean, even during the pump, it may, right? But the data I'm showing you is from the probe. So I pump for seconds, and I wait, and I come with a sub-nanowatt probe. I see the attractive one. Maybe in between, when the pump is on, everything is destroyed, but it gets me where I want to go.
I see.
Okay, further questions? So if not, let's thank Atac again. Thank you very much. And